morning, good afternoon, good evening, wherever you are. Probably people in Sydney are still sleeping right now, so they're going to miss this talk. Well, anyway, so today I'm going to talk about a short paper entitled Rethinking Time-on-Task Estimation with Outlier Detection for Individual Time and Task Differences. So a little bit about me. So I finished my PhD at the Open University, and I just moved to the University of Michigan for my postdoc. So yeah, let's go. So obviously, log data is very present in most of the learning analytics studies. And in a typical log file, you would have the format as follows. So you have some sort of user ID, you have some description about the session that you are interacting with, and a timestamp of that session when you access that session. So time on task estimation is usually calculated as duration between two consecutive clicks. So if I give an example here, so user 111, they click on section 1.2 at 9:32, and then they click to the next session on 9:42. So the sort of time spent should be around 10 minutes for that session. So this is a very common proxy of engagement in learning analytics research, and it's also a lot of studies have been using this estimation for predictive purposes, and the time-on-task estimation has been shown to be highly predictive of performance, of academic performance, as shown in a lot of learning analytics studies. Right, so we have this time-on-task estimation, but of course it comes with some challenges with time-on-task. The first challenge we could think of is that the time spent might not actually be on task, because we cannot always know whether students were studying or surfing Facebook or whatever social media. And also, what is a normal time on task, and how can we detect any anomalous behavior or anomalous time on task behavior? So so we don't know what happens between these two consecutive timestamps between two clicks. And this is a problem in, when we use log data in every cases. So previously, a common approach in most learning analytics studies, including mine, has been using a sort of fixed cutoff threshold, such as 15 minutes or 30 minutes. So if a time on task estimation or if that duration was above this threshold, then we sort of cap at that threshold or just remove the outliers. This approach, it's easy to do because you come up with a number, a lot of people do it, and there's something about a round number which sounds nice when you pick a threshold. However, are all the learning activities homogeneous, right? So the time on task for different activities could be, the time spent on each activity could depends on the kind of activities has been designed. And also, are all students homogeneous, right? So do we assume all students will have the same threshold, or all the learning phases are homogeneous? So these are some of the questions that I would explore in today's talk. So previous work, very popular article of Kovanovich and colleagues tested different outlier processing strategies, different thresholds and different ways to manage outliers. And the results suggest that the choice of outlier processing could really shape the research findings. So the way that you choose to handle your outliers could really affect the predictive power of your conclusion, of your academic performance. So is there really a correct way to handle outliers in Timeontask? So before going into more outlier detection methodological aspects, first we should start with what do we know about learning behaviors. First of all, we know that given the same instructional condition, each learner makes different choices about what, how, and when to study. So a lot of learning analytics studies has explored these differences in learner strategies, right? So you see a lot of clustering approach of log files of learning behavior to identify different learning strategies. The second thing we know about learning behavior is that it is time dependent. So learning behaviors themselves does not always stay constant throughout the course, but there's actually changes dynamically at different phases throughout the learning process, such as at the beginning or when you have an exam or when you have a revision phases. So learning behaviors would change according to different learning phases. And the last thing we know is that the pedagogical design decisions of each task will affect how students engage and how their learning behavior would occur. And a lot of my work has explored this aspect of the effect of learning design on students' engagement. So with that in mind, how could we translate this into outlier detections? So my argument of the whole paper is that outlier in Timeontask should be contextualized. And there are three things it should be contextualized on. First is the individual. So what is a normal duration for each student depending on their own learning behavior patterns? The second factor is the time. So what is normal for that point in time or that learning phases? And the third one is task. So what is normal for that kind of learning activity or that kind of task? So when you have a 5 minutes videos or whether you're reading a scientific article, so that Timeontask is really depends on the design of that task. Right. So outlier detection is something, has a wide range of techniques and have very popular application in other fields such as fraud detection, weather forecast, so you detect whether there's a, like a snowstorm or whatever, cancer detection. So, however, the application of outlier detection methodology in education has still been limited. So outliers we could broadly categorize into three types. So the first one is it's called global outliers. So these are the data points that fall far outside the entirety of the data set. So imagine if we have a 8 feet tall man or woman. So this person is just way taller than everybody else on Earth, right? So this is called a global outliers. The second type of outliers is called contextual outliers. So the data points that deviate from the rest of the data points within the same context. So if you take the context of an NBA team, then probably a 5 feet tall woman or a man would be an outlier in that context of an NBA league, right? Because everyone is like 6 foot above, right? Whereas a 5 feet tall woman or man in a more normal population would not be considered as outliers. And there's also a collective outlier. So there's a subset of data points that are not anomalous in either global sense or contextual senses, but as a collection deviates from the entire data set. So we can imagine these as the whole NBA team. So the whole as a group is a collective outliers because they're just pretty much taller than everybody else, like a normal person. Right, so in this study, I'm going to try to focus on contextual outliers. And as I mentioned before, contextual outliers based on individual time and task differences. So these are the research designs. So first I collect log data of the course in a distant learning institution. I'm going to compute time on task estimation as the time differences between 2 consecutive clicks. And then I'm going to test different outliers detection methods. And then I'm going to aggregate time on task per student as a proxy of engagement, correlate that engagement measures with final grades, and then compare the predictive power of different outlier detection methods. So the context of this study is a second-year course in a distant learning institution. There's about 273 enrolled students from October 2015 to June 2016, so that's roughly 9 months. So we have about roughly 450,000 time on task estimation. So as you can see on the screen, each dot is a time on task estimation. And I'm going to go a little bit deeper into this figure later on. So outlier detection methods in the literature. So if we look at the literature in outlier detection methods, you have the first one is a very simple one. It just use a fixed cutoff threshold, right? It's like 10 minutes or 20 minutes. The second could be distribution based. So you identify the outliers based on the distribution of your data. So you have interquartile range, or you can use z-score or standard deviation from the mean. But there's also a plethora of other methods, such as distance-based method, density-based method, decision tree, and so on. So these are really machine learning or very advanced outlier detection techniques that have been used in other contexts. So in this study, I'm going to use I'm going to test out a few outlier detection approaches. So the first one is just to use 3 cutoff thresholds, 60 minutes, 30 minutes, 10 minutes. And then I'm going to use one of the distribution-based methods, which is interquartile range. And then I'm going to use the other one, which is a more sort of machine learning driven called isolation forest. So just a little bit background about isolation forest. So, you know, isolation forest is a sort of a random tree family type of methods. So the idea is you have a bunch of data, you carry out random partitions, so you carry out random slices of the data, and if a data point, if it's normal, it will take more slices or more partitions to be isolated, whereas anomalous data point will take less slices to be isolated. So that's the idea, right? So you slice the data randomly, so the data point which are more likely to be anomalous will just take a few slices before it was isolated. So in order to account for time, for individual time and task differences, let's say X is the time on task of individual I in week J on task T. I'm going to compute a threshold using an outlier detection method for each student. So let's say in this case I have 300 students. I'm going to compute 300 individual threshold for each student. I'm going to compute a threshold for each study week. So this has about 30 weeks long. So that's going to be another 30 study weeks. And then for each task itself, right? So the idea here is that an observation or a data point is considered to be an outlier if it's above all 3 thresholds, right? So a data point, because sometimes a data point could be an outlier for, let's say, for a student, but within that week or within that task is actually a normal durations, right? So if you think of an exam week, then the time spent or the time duration in that week will be much more, much likely to be higher than the rest of the course. So that could be an outlier, but for that week, it is not, right? So it depends on each learning phases. So how can we, compare the performances of different outlier detection methods? Because this is an unsupervised learning problem. There's no ground truth labels, so we could not see what students were actually doing on their laptop or their devices. So we have to work around it a little bit. So I followed the approach of Kovanovic and colleagues in 2015. So the assumption here is if time on task is correlated with academic performance, then a good outlier detection method might reduce the noises in the predictive model. So you typically would observe a higher R square. But obviously, this is just an assumption to derive some proxy to compare different outlier detection methods. Right, so let's look at the results. So this is the same figure as above. So each dot is a time on task estimation. As you can see, it has a wide range, right? So from 0 to even thousands of hours, right? Because when you click and then you haven't been active for a month, and the next month when you come back, so that duration would be much longer. But in this case, I just kept all the duration under 12 hours, and I removed the rest because, yeah, above 12 hours is a bit is already a global outliers in a sense. So when you look at this graph, you can see that obviously there's a lot more dense in the lower range. So a lot of time on task is within a small time unit. But you can also see there's a wide range up to an hour, 2 hours, 3 hours, and the higher you go, then the less likely that you would have that sort of duration. But if you draw a density function throughout this timeline, then you can see that the density actually changes over time. So it's not always constant, right? And if we just draw a horizontal line across this observation as a fixed cutoff threshold, then you would probably overestimate and underestimate some time on task estimation at different learning phases. So here, that's what I did. So I tested 3 different thresholds, and then I used a interquartile range approach, accounting for individual time and task differences. So for each individual, we compute a threshold based on the interquartile range, the same for each study week, and the same for each task difference. And the orange bubbles was identified as outliers, and the green bubbles is our normal estimations. So you can see, okay, so if we pick a 60 minutes threshold, then obviously we underestimate a lot of outliers. So you still see a lot of orange dots still below this 60 minutes thresholds. At 30 minutes seems to be a better, more reasonable. And the 10 minutes, then we overestimate the outlier. So actually, these dots could be considered as normal estimation. So the idea here is, I hope that hopefully have shown, is that what could be considered as normal is really depends, at least depends on the learning phases in this case. So the next step I did is to run a normal regression, very simple regression with time on task as the dependent and final grades at the academic performance. And these are unstandardized coefficient. So if we convert this into standardized coefficient, that would be about 0.5, roughly 0.5 standard standardized coefficient. So, but the most important things here is we want to compare the performances of each outlier detection methods. So here you have the adjusted R-square. So there doesn't seem to be much difference in terms of predictive performance between 10 minutes, 30 minutes, or 60 minutes. The interquartile range, so if you just compute an interquartile range for the whole data set, and if you compute the interquartile range accounting for individual time and task differences, then you can see that the best performed model was the one that accounted for those three factors. And it improves the R-square by roughly 4% and 3% compared to the cutoff threshold. So the I4S surprisingly had a poor performance in this case. So I run the I4S for the whole data set and I4S for accounting for those three factors. So again, we also see an improvement in predictive power when we accounting for time, task, and individual differences. But the algorithms as a whole actually perform poorly compared to even using a fixed cutoff threshold. Right. So the conclusion in this case, so we see an increase in model performance when we account for differences in individual time and task. So you can see here the best performance model has 3 to 4% increase in R-square. There wasn't much differences between 10, 30, or 60 minutes in terms of R-square. And isolation for us, surprisingly, despite is the most complex or most sort of data-driven, and it's very computational, heavy computationally. It has the poorest performance. So this comes as a little bit as a surprise because isolation for us has been shown in previous comparative studies of different outlier detection methods. It has been considered to be one of the most, the best performed and very stable performance. But in this case, it has the poorest performance. So the limitation of this study, the first one is that we don't have obviously a ground truth and probably never will because due to privacy issues. So the study was conducted in only one course in a distance learning institution. So the results could vary in different courses or different learning settings. And there are many outlier detection methods that I've talked about that have not been tested. So this is going to be a future work to carry out a more comprehensive comparison of different outlier detection methods to process time-on-task estimation. So I hope in this talk there's a few takeaways that I would like to mention. The first one is that I think learning analytics studies, when using time-on-task estimation, should explicitly report how they chose to process these estimation, right? Because a lot of studies was very vague about how they handle this time-on-task estimation. And we know that the decision that they choose to process outliers could affect the study's conclusion. And hopefully in this talk, I've sort of convinced you to use what we know about learning context, learning behavior, learning theories to actually contextualize outlier detection methods instead of using a fixed, easy way, like a fixed cutoff threshold across all the data points. And what is normal duration or what is a normal time on task really depends on each individual learning patterns, the nature of the task involved, and the learning phase in the course. Right, so that was it. I think we did pretty well in terms of time, and so